Thank you very much for inviting me to give this opportunity to give this plenary talk. I'm going to give you an overview of the analysis of complex heterogeneous data. I will just focus on a subset of kind of complex heterogeneous data. I'm sure that everybody here has a kind of different idea of what a complex heterogeneous data is. I'm trying to give you an overview of my approach with, I think, a very interesting application that is brand new, so excuse me especially for the last plot that I'm going to show you about this. So probably here there is plenty of people that are very expert of plotting and can also help me in doing nicer plots. Okay, so this is what everybody should do. I'm a statistician, so I see everything into a statistical framework. So I'm always interested into modeling the data and assessing the uncertainty. So we all know that we have some data. We need to do some exploratory analysis on our data. And some people can also be happy just with that because they may realize and may discover what they were interested into. But in general, we also may want to fit some model. The model needs to be useful and flexible. And this is not always easy to do when we have complex data. Then we also need efficient computation and also stable computation. And again, when we have complex data, even if the data set is not huge, we can have issue about the computation. And we are going to see some example. And also we need some stable computation. So I think I'm going to use a particular approach for the computation that is called variational inference. That is an approximate approach for the inference. So we need to realize that we are using an approximate approach for the inference. It's not bad to use an approximate approach. I'm not saying that. But I think we should be aware of it. Sometimes it's the only solution we may have if we want to have a solution in a couple of seconds, a couple of hours, or a couple of days. If we are able, and if we want to wait, we can wait a year for our code to run. We may decide to go with more exact algorithm based on simulation, for example. So this is a compromise that we may need to make, but I think, and I think we should be aware of it. And then, obviously, we need a software. Ideally, an R package that needs to be user-friendly because we want to share our research and our efforts with all the people. Also with the people that are just interested in applying the code for their own data set and they don't know much about statistics and the model and the inferential approaches. So we need something that is user-friendly, at the same time that is customizable. So if there are some people that want to improve the software, we can improve it. We can all work together into improving the software. Or also if they want to check what is going on into the software, so why the results are different from different approaches or softwares. So now I'm focused on the first box, so the data. So what I'm focusing in is extracting knowledge from large, heterogeneous, and complex data sets. And this is one of the main objectives of statistics and data science. Now we have access to tons of data. But what we want to do is to be able to understand what is their meaning. Because this data set can be complex, there may be a lot of dependencies between our data, there may be the presence of missing data, and so how to handle them. Not just remove everything that we don't like, and so we are losing a lot of information. So for example, we may have one example of classical heterogeneous and complex data are spatial data. There are models for spatial data. Another case may be relational data. So there may be some relation between our observations. Or we may have spatial and relational data. So this is also much more complex. Then we may also add further sources of complexity. For example, also a longitudinal data. Or we may observe different relations between our data. And the spatial position may stay the same if we are, for example, considering our observation to be a city. They don't usually move the city. But if we are considering the spatial position of one person, can move around over time. So this is for the source of the heterogeneity and complexity. The data set that I show here is not just a random plot, but I decided to show you this map, and you can notice that this is the south of Italy and the northern part of Africa, because the data set that I'm going to show you and to use for today's talk is about the human smuggling out of Libya. In 2013, it exposed this problem. There's been this huge Lampedusa disaster, the first huge disaster of a boat sinking from the way from Libya to Italy. Now you can read that there is this problem that is continuing. It's continuous, going on and going on. But from this disaster, the Italian police started an international operation, series of operations called Glauco 2, in order to discover who are the main human smugglers. And in particular, I will focus on the operation that is called Glauco 2, and it's about the phone calls. They have wiretapped the phones of 26 suspects. No, 29 suspects. Should check. I will check that later. Anyway, they checked all the phone calls that they made and they received. We have all the transcriptions. The main problem is that the Italian police provided us with the transcription in Italian. But most of the smugglers speak into different African languages. And so you can expect that this translation and this transcript are really not very reliable. So for this start of this project that I've been involved to very recently, this is a collaboration with a lecturer in criminology from the University of Cambridge. And he was telling me there are no good statistical method for this kind of data, for this kind of complex data, even if the number of observation is quite low, so it's 29 people. But then this dimensionality explodes, because we have all the records of the phone calls that they made and received. So they called a lot of people. And we're interested in to discover who are those people that they called. Are they just their mother, their relatives, or since they decided it's expensive to check the phone calls of some people. So they were already suspect, so they were very likely to be connected with the smugglers. And also, a good thing about this data set is that this operation concluded in 2014, and they arrested most of these people. So we are able to now create a model and check if what we discover is meaningful or not. And then what we want to do is to create this model and generalize for the new operations, or in general for the operation of phone of wiretapping. And so in order to predict who are the suspects, who are the big bosses, who are the smaller smugglers that are going to the boat and just makes the travel for the people, and who are just the other people they don't have to care about. So this is kind of the map. So most of the people start from Libya. Most of the people start their journey from Eritrea, actually, and then they travel to Italy. In particular, they usually land in Lampedusa, that is the small island over there, or Sicily. And then they go through Italy, and then they go around the world. So this is, as I told you, the operation Glauco 2, and we start to translate this problem, this practical problem, into a statistical problem. So in this way, we are able to build up the model. So we started to say, okay, we have these 29 people, or better, 29 phone numbers. So phone numbers may belong to, two phone numbers may belong to the same person, but this is not the case. And so these 29 people, we call them ego. And then since all of the other information are coming from these 29 ego, the people who have been called by those people are called alters. So this is the kind of structure. So we have more than 15,000 alters. And also, we know that most of the egos share some of the alters, because there are some models for ego networks, but usually they don't allow a lot of overlaps between egos and alters, and most of the egos are connected to each other. So this is the kind of structure. So now, what I would expect everybody to do always is, when they have the data, they transform it into some sort of structure that can be analyzed. So in order to understand what is going on and what are the properties. So we have the ego that are connected. We use the red line just to show that the relation between the egos is different from the relation between the egos and the alters. And the reason why we consider this relation different is that we know a lot about the egos, but we don't know much about the alters. This is a kind of information about the investigation period. So actually, the first ego to be wiretapped has been ego 07, that has been started to make calls on Christmas days. And then they go on, all the investigation goes on until October 2014, when they arrested some of them. I indicated the ego with the first one. I used his first name, that is Amare, because I love that name, because in Italian, amare is to love. And then we are going to see that he behaves in a different way with respect to the other egos. Then the other, I've just labeled them ego E01 up till ego E11, because we know a lot about those egos, and U01 until U10 are some unknown. So we have less information about those egos. But we want to keep all of the information that we can. This is the kind of the length of the phone relations between the number of calls. Because what we argue is that if you are a client of a human smuggler, you're likely to call a lot of time the smuggler just in the day before your travel. And then you stop. So you will have a very intense but short relation with the smuggler. If you are another smuggler, you're expected to make a lot of phone calls with the other smuggler for a long length of time. And then there are the kind of random phone calls that we consider to be in the middle. So this is a kind of relations. So the first one is about the calls between the egos, so between the big bosses, and the second one is between the ego and the alters. And you can notice that the number of phone calls is usually extremely high. And especially we can notice this into this one. This is the average number of phone calls. The average number for a lot of people of phone calls during a day, a single day, for most of them is more than 20. I think if you have a partner, a boyfriend, or girlfriend that calls you 20 or more times a day, will be really upsetting. But you can consider that in this case, they make a lot of phone calls. So there is also a lot of information about the intensity of this relation. Then we decided to go and have a look, have a plot of the network of the ego-ego. So we can plot the network, or we can use this kind of approach that is an heat map. So there is a black square if there is a relations. So there has been at least one phone call between the two egos, and it's gray if there is no relation. And you can notice that Amare is not connected with anybody. So he behaves on his own. You can also notice that N, I use this notation that capital N is our number of egos, and 169 is the number of edges. So it's the number of a black square. And the density is the proportion of edges in the network. So it's about 42%. Then we can also use an heat map of the incidence matrix. So in this case, we have, in the row, we have our egos, and in the columns, we have all of our alters. So this is the kind of thing that we can visualize. It's very hard to visualize from this one, but it's even harder if we try to plot everything together. So M is 15,793 is our number of alters. and we have a density of about 5%. So this graph is extremely sparse. Okay, so now we put the data together and see, okay, what we have. We have y, that is the red square on the top. That is our adjacency matrix of the relations between the egos. Then we have the blue rectangle that represents the relation between the egos and the alters, and the gray square are our missing data, because there may be some relations between the alters, but we don't observe them. So you can observe, you can notice how much missing information we have here, and this information may be very important. So what we have done is we started by analyzing our ego network of Y. So our subset, just the behavior of our big bosses and the relation between themselves. So our data is called Y, and we use a latent space model approach. So Z is a latent position in a Euclidean latent space. Let's just focus on a two-dimensional latent space. In this model, we have our two-dimensional space, and we assume that two egos, if two egos are close in the latent space, they are more likely to be connected than two people that are more far apart. Okay, so we want to use a probabilistic approach to model the probability of a link, of a connection. So this is the model that we use. So we have, let's see, okay. We have this kind of model, and I think it's quite easy to understand because there is a relation, this one, zi minus zj squared, is the square Euclidean distance between the position of node I and node j. So it's the distance between two egos in this latent space that we don't see. And then we only have another parameter that is called alpha, that is related to the density of the network. So it's telling us how much, so it's telling us even if two nodes are overlapping in a space, what is their probability to be connected? And you can notice if you put this difference to be 0, that is equal to the exponent of alpha over 1 plus the exponent of alpha. So it's not 1, the probability if two observations are on the same position. But there is some probability. And we use a Bayesian approach, so we put some prior on our parameters. So what does it mean to put a prior on our Z? Just focus, for example, on the case when sigma squared is equal to 1. So we are working with a two-dimensional multivariate standard normal distribution. So in practice, it means our prior is that there is a probability of about 99.8 that our observations are lying around a circle of diameter 3, of radius 3. So this is what it's telling us. It's telling us how wide is a circle, because we are using a normal distribution with diagonal metrics. And in practice, we are setting up a space where there is this likely, where the observations are much more likely to stay. The problem with this model is that we cannot fit, it involves, if we want an integral that cannot be evaluated analytically. The usual approach is to use Monte Carlo methods, but they take a long time. There is the latent net package that fits this model. In particular, the latent net package fits the model with the Euclidean distance, not the squared Euclidean distance, but it takes a long time. Now it has improved, but I still remember when I was doing my PhD and I started to work with, I downloaded my Facebook data because we were able to download our Facebook data. I decided to analyze it. I ran the code. It took a lot. I said, OK, let's go home and come back tomorrow. It was still running. I said, OK, I should stop. And I had just like about 150 friends. So it wasn't a huge network. And so we need something more efficient. So this is the reason why I propose to use the variational approach. So the variational approach, we are imposing the family of distribution that our posterior distribution follows. So in particular, in this case, I'm imposing that we are imposing that all the positions are independent in this Latin space, and that each position follows a normal distribution. So in practice, what does it mean? It means that in the posterior, so given the data, each one of the observations will be no more free to go around of our circle of radius 3, but can just stay in a position depending on the value of Zi, so a particular location, and and can go around to a smaller circle that is about sigma tilde. So this is our posterior distribution. This is very informative because it's telling also about how much information we can gather for the data. Because from some data set, we may have this sigma that is very large. So in practice, there is no information. We can fit the model, but we are not gathering any information. And in other times, most of the times, we are getting information. So we are able to visualize if there are some clusters in our data, or we are able also to handle quite easily missing data and to estimate the probability of a link because we are able to estimate the latent position. So now I explain you super quickly, just for your curiosity, how the variational inference works. This is true in general, not just for this case, and this is a figure that is very common in most of the books about variational inference. So in practice, we have the true posterior distribution that is this distribution here with this irregular shape. I actually took this distribution from the output of the MCMC in a small case. And then, so we have this distribution that exists, but we don't know how to calculate. And then we decide a family for our distribution, for our posterior distribution. For example, in this case, we decided to use a normal distribution. What the variational approach does is it finds the best parameters of the normal distribution, in this case, that fits the target distribution better. We use the Kullbaum-Leibler divergence between the two distributions in order to evaluate how close are these two distributions. So we want to minimize this distance. But we know that this distance plus a lower bound are equal to the marginal log likelihood. And this, you can notice, even if you don't know what it is, you can notice that here is just a function of y. So it's just a function of the data, no more of the parameter. So this one is fixed given the data, and maximizing this quantity corresponds to minimize the divergence. So this is how in general works. So in practice, instead of having an inferential problem, we are working with an optimization problem. Now I'm comparing the results. So I'm finally show you something about R. And so I'm comparing the results given by LatinNet, that is the package developed by Krivinsky and Hancock. And it works with the Euclidean distance. OK, I didn't say why I work with the square Euclidean distance. The main reason why I decided to work with the square Euclidean distance is that I am assuming that the posterior distribution are normal distributed. And the square Euclidean distance between two normal distributed variables follows a chi-square distribution. Otherwise, the Euclidean distance between the normal distributed variable follow a chi distribution. And it's much harder to work with a chi distribution. There are other approaches that perform variational inference with the Euclidean distance, but they require much more approximations, so further than the usual approximation made by the fact that we're using a variational inference, they require many more approximation. While using the square Euclidean distance, we need less approximation in the inferential approach. And then I'm going to show you that also it works better. So the first one uses a different model and a different inferential procedure. So the MCMC, so assuming to be approximately correct. My package is called LVM for net, so latent variable model for networks, and use the square Euclidean distance and the variational approach. This is just a comparison. This is not the best plot. I'm showing you also nicer plots. But what you can notice here is that in LaTeX it takes already, if it's quite small since it's just 29 observations, 10 seconds. And in my model, it took less than a second, even if I'm working with 5 stars. Because the problem with my inferential approaches is that it's sensitive to local maximum. So you need to rerun it a couple of times in order to get to the true maximum likelihood. Then this is what we usually do. So this is an approach to visualize the network, but how can we say if this is meaningful or not, if this is correct or not? The usual approach with networks is to use a goodness of fit approach. So we know about some characteristics, some statistics of the network, the degree, the edgewise shared partners, so how many observations shared apart, so how many partners share a couple of an edge, how many couples share a dyad, and a form of distance, so the minimum geodesic distance. On the top, there are the results from LaTeX, and on the bottom, from my model. So this is why I also said that the square Euclidean distance works better, because what we want is that the continuous line, in this case, the red line on the bottom and the black line on the top are the same, that we want that they are between the 95% confidence interval of our box plots. Because our box plots are given by 100 simulations of our data. So because we have the posterior distribution, we can simulate network, and we can calculate the characteristics into these networks. OK, so this one, I think, is a nicer plot. And this is about, OK, so here is just the result, the output given by my package. And you can notice the gray ellipses. These are the variances of our posterior distribution. In particular, these are, the 95% credible intervals. So we know that there is not too much uncertainty about the position, because we know that there is 95% probability that they are within those ellipses. And we decided just to color in order to explore our data set. We didn't use the information about the contact with Libya of our people, but we have this one. And we just used to plot the data and to know more about the data. And we can notice a lot of interesting information. For example, what we are mainly interested is into understanding if the unknown have contact with Libya or not. Now I'm working on some new models. I still don't have the results, but we can notice that most of the people, most of the big bosses, so most of the people that have contact with Libya are next to a person that has no contact with Libya. For example, this happened here. So we are able to visually get some information. And also, we can notice that our unconnected person has a contact with Libya. So probably it didn't need to have another contact with Libya between our suspects. Then we have other information that we can use. For example, the role of our smugglers. We know that some of them are organizers, so are the big bosses, and some of them are aid. And again, we can see that usually organizer and aides are next to each other in this latent space. So this is super quick comment. This is a general comment about the variation versus MCMC, so it is valid anytime you incur with this kind of variational inference approach. You know that we have seen that the advantages are that we have closed form posteriors is way faster than MCMC methods, so we can in general also use them to explore the model space. In this case, we have just focused on a two-dimensional space while we want to explore more dimensions or different kind of models. And also, we know that another advantage is that in the absence of posterior dependence, the lower bound will match the log likelihood. A problem is that it's difficult to assess how tight this lower bound is. As I said, it's also sensitive to the starting value, so we may need to restart the algorithm a few times. In my experience, for my variational inference, 5 times is more than enough, most of the times. And then, so this may be useful also for larger network, or if you want then to use MCMC, you know where you can start to explore the parameter space. OK, so we are coming back to our ego-ego network, because I show you a simplified version, but we wanted something for complex networks. So in this case, we have also X. So we have a Y, that is the relations between the egos, and and X, that is represent the relations between the egos and the alters. So what we consider is that we have this latent position of the egos that stay the same, and then we have another latent position of the alters that influence the value of X. This is just to write down the model. So it's similar to the previous one. This one is like the previous one. And we have just added this part. So we can use a variational approach similar to the previous one, and we can obtain the results. So in order to do this analysis, we have removed all the data connected to Amare. The reason why we have removed it is that it's not connected with any of the other egos, and all of these alters are not connected with any of the egos, of the other egos. So it's completely unconnected. So we may decide to analyze it separately, because there is no reason to analyze it together with the rest of the data set. So now the data set is slightly decreased, so we have 15,695 egos now and 28 alters. But we can also notice that there are just 1,290 different connectivity patterns in X. So by noticing this, it means that there are some people that call the same person, exactly the same set of egos. Noticing this highly improves the computation times for this case. Because we know that if 2 people behave in the same way, with this model, they are coming from the same distribution. So they will have the same mean and the same variance. So the same position. So this is the result. So this is why I told you to excuse me for this weird plot. The red dots are our egos, and then we have plotted our alters. So we can notice that there are some alters that are much more important and included into the center of this part. So they seem to have a much stronger relation and a stronger important role in this network. We are still investigating. These are just some preliminary results. So we still have to understand well and to go more in deep in order to visualize what is going on here. And the good news is that by using the variational approach, there is no problem in fitting this one. It takes less than a second also with all of our other alters. And this model is not yet implemented in LVU for net. But now I'm going to show you another kind of complexity. Probably those of you who have worked with network have already seen this network thousands of times, probably. And I think this network, if you are going to start to work with network data, is a kind of the starting point. Because I think if it doesn't work with the Samsung dataset, your model or your approaches, probably you're in trouble. Because usually everything works with this network. This is small. We have 18 monks. And so Samsung went to this monastery and analyzed the relation and asked to 18 monks in a cloister in New England about the relation, who they dislike, who they esteem, who they have positive influence to, who they praise for. And we know about a lot of relationships between our monks. He has been lucky enough to state that during this day there has been a crisis in the cloister. So it happened that there has been the expulsion of 4 monks and the voluntary departure of several others. And then the monastery shut down. So we probably also, having this information, we are able to interpreting our data. Because I think the starting point, always, when we are trying to develop a new model, a new method, is to work with something that we can interpret, that we can check if it's true or not just guessing and exploring something that is completely new. So what we are working on in this case is that we analyze 3 positive relations between the monks: the esteem, the positive influence, and the praise. So this is the latent space model for the results for the 3 different relations. I colored with the classification according to Sampson. And we can notice, for example, that here, for the praise, there are a much lower number of edges. And this causes the fact that the credible interval are much larger. Here there is more information, it's more dense, there are more relations, and the credible intervals are smaller. Now, we see the colors, and we can notice that, okay, this tends to be, the red tends to be together, the black one tends to be together, and the blue one tends to be together. But it's a bit, I think, cheating, because it's helping a lot the fact that we have the colors on the network. And it's not always true. What we wanted to do is to analyze these networks simultaneously. So my package also allows to analyze all of them together. The main assumption is that there is a positive dependence between the relations. So you cannot just jointly model any kind of relations together, but you have to model some relations that are positive dependent. And because we are assuming that they are coming from the same position in the latent space, so we have a unique position that causes all of these different relations. And this is what we obtain. And in this case, okay, the colors helps again, but we can notice that the credible interval, the 95% credible interval, don't overlap at all. So this one is completely separated from this one, and this one, let's include also the green one, is completely separated from the other 2. So in this case, we are able to visualize the clusters. This is a toy example. But in general, so we are also able then, if we want to fit other models, or if we want to fit some model with clusters, we're able to kind of already see how many clusters there may be in our data. Also maybe to limit the exploration of the space, of the model space. A good news of modeling all of this information together is that we are able to handle very easily and very well the missing data. In networks, we may have what I call 2 types of missing data. The missing links, so there is just a link that we don't observe, or the missing nodes. With the missing nodes, it means that in one of these 3 relations, there is no information about one node. So we don't know, for example, if the last if the last monk has prayed for anybody, or if anybody has prayed for the last monk. And this is quite common in practice, that we may have no information about some characteristics or some relations of our data. So for the missing links, we have a very low, these are the misclassification rates. We have processed a 10-fold cross-validation, and we can notice that even if we fit the latent space model, so we fit a model separately to each network, it's about 2%, and in latent space, in the joint modeling, so modeling all of the relations together, is even lower. In the missing nodes, if we don't observe a relations of any information about one monk, we can do anything by analyzing just one relations. But given the fact that we assume that there is a positive dependence between the relations, we can use the latent space joint model. And we can notice that the misclassification rates are extremely low. This is also due to the fact that these are highly correlated and connected and positive dependence, the 3 relations that I'm using. If by any chance you decide and you do a joint model between 2 relations that are like love and hate. What would happen here is that, first of all, the variational algorithm will stop at a maximum of number of iterations that has been set up. Then you can decide, OK, I will plot it anyway. You can plot them. And you will realize that the confidence intervals are covering the time space. So it means there is no information. So this is also something good that I think we can try to think of, all of us, that when we develop the model, if a model is wrong, some way to make the people realize it. Or especially to realize the importance of the uncertainty. Because a point estimate can be obtained most of the time. What is important is that this is meaningful. So there are small confidence interval, credible interval, or whatever you're using. Or at least a way to observe and to make the people realize the importance of the credible interval and confidence intervals. OK, now I said that my model works for larger data set, and I'll show you a data set of 18 nodes. So now this is another work that I'm currently finishing to write up, and it's about the network interaction of 80 experiments on 15,000 yeast proteins. So this is the plot of the network. In this case, it's not so important to plot the network. It's not so meaningful. I'm sure that there are ways to plot the network that looks nicer. But the good news about this model is that there is a certain probability that two proteins interact. And this is particularly useful if you're checking if two proteins are interacting by experiments and by looking and trying to do them. You may have a lot of missing information. And with this probabilistic approach, you're able to estimate the missing link and to calculate which pairs of proteins have a higher probability to be connected. So this is very informative for, I would say, the identification of missing links or false data, and not so much to visualize the network. And in particular, you should notice that here there is this nice rainbow here. And this is just due to our starting point and to our prior distribution. Because if you are going to notice it, and if you check, now I haven't put the scale of the axis, but these are all at about 3. So where is the 99.8 probability that they are given by our prior? So our prior distribution in practice gives us the opportunity to have all the unconnected proteins here in a plottable region. Because otherwise, if you don't put the prior, or if you put a very large prior, in order to maximize the likelihood, these unconnected parts will be put infinitely far apart from the center. And you can imagine that you will obtain something that is completely not informative. This plot on the right, I've used a similar approach to the previous one, to the multiple network views, but in this case, I've jointly analyzed the network and some nodal attributes. Because the biologist told me that the results of these experiments are positively correlated with the probability of a link. So this is why I put this one. And the good news about this is that these dots here are no more put randomly, but they are closed in the space if they have similar results into these experiments. So there is kind of more information, and here there is more highlighted a clusters, a very dense clusters in here. Then, another minute, I've almost finished. There is another work that I've done, and it's about not just the use of variational, but in general about the quick approaches. Sometimes we may just need upper bound to provide some efficient approximations. For example, depends on our question. I've done this work, and the Taylor's package is about evaluating the risk of insolvency by estimating the probability of the upper tail of the aggregated loss distribution. So this loss distribution, so the problem here was that we have a set of events, the probability that some events happens, in particular that some hurricane hits, and the loss associated to them. And we want to know the distribution, the aggregate loss distribution, so the distribution of the losses in 1 year. The problem here is that we don't know how many events will happen in 1 year. We don't know which one will happen, and the kind of also the loss connected to the event may be also a random variable, so may varies. So this is why, for example, we use some upper bounds from probability theory. So we know that it takes a lot of time to calculate this quantity exactly by Monte Carlo simulations. The problem also in the Monte Carlo simulation is that in the upper tail, that is where we are more interested into, there is a very high variance. By using the upper bound, we can just say, okay, the probability of loss, an annual loss greater than 35 million is less than a certain amount. And this may be useful, because if you say, okay, I'm an insurer or reinsurer, and my capital amount is this one, will I be able to cover the losses? And in most of the cases, here you may say just, you look if it's lower than your upper bound, and you're sure that it is, like that. Otherwise, with the Monte Carlo simulation, in order to get the very high probability, the very high tail, it will take a lot of time, and you will have to run a lot of simulations. And a big advantage also of using upper bounds sometimes is also to perform sensitivity analysis. So what happens if for example, they give us some estimates that are 10% less than what actually is? Will it change dramatically or not? With the upper bounds, we are able to do this kind of investigation instantaneously. So say, okay, let's just try how much should I be wrong to make huge changes. And so this is something else that is very important. Okay, so here I've just almost finished. These are just the 3 main packages that I've developed. So the latent variable models for networks is the one that I'm currently also updating in order to then be able to have a suite of models that are able to flexibly model a large kind of complex heterogeneous network. Then there is the tail loss package for the probability in the other per tail of the aggregate loss distribution. And then I've also contributed to the GW model package. That is a package about geographically weighted models. So geographically weighted regression, principal component analysis, and so. It's been quite a while since I've worked with the GW model, but my co-authors told me that it recently increased a lot its speed. So if it has been a lot that you haven't worked with the GW model, maybe because it was too slow, now it has increased its speeds a lot. Okay, so just to conclude and come back to our suite. So what I hope that I make you reflect today is about the importance of the data and the complexity and the heterogeneity. The importance also of a statistician to go and to talk to the people who has the data and have more interest in applications, and also for the people who have applications to go to the statisticians. Also, we need to do new models, flexible modeling, and useful modeling, and computation. So I think also in this part, we don't necessarily have to be alone. I think we can also collaborate and try to make this one as nice as possible, as good as possible, and as useful as possible. So to perform new models, new computations, and new software. And always giving feedback about all of these steps by end users and experts. And that's it. Thank you.
Are there questions?
There is one over there.
Okay, there's the light, I don't see it.
Thank you very much for this interesting talk and the many interesting applications. When you show networks with these confidence ellipses, or actually high density, what about you mentioned the problem sensitivity analysis or something. What about your prior distributions and all the assumptions? How can you assess the uncertainty of that part?
I tend to use small kind of assumptions. So for example, in my case, it's more about the dimensionality of the space. So I focus here on the two-dimensional space because we have seen that it's nice to see a network in 2 dimensions, and in general, it works very well also in terms of goodness of fit and other approaches. We can also play with our prior distribution. So the sensitivity to the prior, but is usually not too big because the network is very informative. The network has a lot of information into that, and we are keeping all the information by using this Latin space approach. So this is a kind of also advantage and disadvantage of a position for each observation. Because for each observation, we have then to estimate this position, so to give, for example, a two-dimensional position for that, for all of the n parameters, for all the n observations. So that we can also consider this Latin space as a known quantity, so we need to estimate them. So this is also why, with respect to other approaches, maybe was low. But the big advantage is, yeah, about the uncertainty. But in this case, it's not too sensitive about the choice of the prior, in my experience, but it's hard to say, yeah.
So let's thank again Isabella Golini for her very interesting talk.
Thank you.